Hello, my friend, and welcome. So we continue today with a new recording, still concerning the introduction of the Proland library into my own engine here in implemented WebGPU. Yes, we'll be reviewing a bit some of the progress that I made. It's still pretty far from being completed. Actually, it's really tricky and it's still a work in progress, and we won't really show anything visually interesting here. We are mostly going to be reviewing some code implementation. And yeah, I mean, we have to do it anyway. That's the initial step. And let's just try to get through this, and we'll see how this goes. Let's switch the screen first. Okay. So as usual, I'm using the notes I have taken so far in this implementation as a base for, reviewing what was introduced lately. First thing we need to discuss is, yes, the support for, this kind of format. This is basically an R float format, in case you're not familiar with that. So you're using only 16 bits to represent the float value, whereas normally a float will be using 32 bits. So the thing is, in Proland, we have to use the reference implementation I'm using. We'll be using this this R float format. For instance, if we focus on the ElevationProducer, which is actually the main focus that I have currently, I have been implementing the base time producer class, all the base classes, and now we're really starting to move to the actual higher level implementation stuff. So the ElevationProducer is one of those, and it's why it's a bit complex to implement that. So we have, for instance, in this one, a function here which is going to create a texture to the array, corresponding to some kind of DEM noise. DEM is a digital elevation model, basically, I think. And you're going to produce some noise value here as a texture to the array. And if we bypass all that, you'll see that eventually when it's time to create a texture, it's going to be using this format. So single channel, the red channel, and then storing the R float values in the 16 bits only. And so I wanted to figure out how I could handle those float formats in my own program, because I know it's supposed to be supported in WebGPU, but I have never really been using this, so it was not really obvious for me. So what I did was to try to create a unit test, actually, to figure out if it was working as expected. But before doing that, not really before, while doing that, I needed a way to copy a texture to a buffer. Really? Let's just try to check the unit test first. So in my home code here, we have, it's spec. So yeah, this is a test I created to verify that support for this format was working fine. So what do we do here? We just create a 2D texture of a given size and this specific format here. And we want to be able to copy into this texture and use that as texture binding, and also copy from this texture. Yes, I think this test was only meant to upload some data on a texture, don't do anything with it, and just download this data again and verify that what was uploaded is still matching was what was downloaded afterwards. And so what we do is we prepare some data. And this is the key here. I guess when you're using WebGPU from a browser, maybe it's different. Maybe you can just pass an array of full float values and it's going to be converted properly. I have no idea actually. But when you're using C++ here for interacting with WebGPU, the native version of it, you can't really try to upload float 32 values into float 16 texture format because your data, what you're going to upload, the size of what you're going to upload is expected to match the size of the destination. So it's we're just creating the texture here, and then we do the write here. But when we do the write, we apply the texture, the data, and the extend give the size of the data. But considering that each element that we have in there is matching what the texture is expecting, is this really a concern on WebGPU itself, or is it from me? Let me check that. Okay, so I've just tried a small change in my unit test to try to figure out if I was dreaming or something. So what I did was to replace the vector format here with plot32 format instead of the R format. And we're just going to provide this array to write the content of the texture. And also, when it comes to do the writing, I have updated this function because normally this would be using the format that you have in your current texture target to figure out what is the size of each element that you're providing as input. And so if you use that, normally you would get only 2 bytes per element because we are targeting float 16. And so I'm just multiplying that by 2 for now. This is something I don't want to keep, of course. And this would be used then to figure out how many bytes you have per row in your buffer when you do the copy. So right now, the system will know that we are providing 4 bytes for each element in the source buffer when we want to do the copy. But if we use that, in fact, it's not going to be a validation error or anything. It's going to accept that. But in the end, when you try to read data back from the texture and compare that with the initial data, you get completely wrong values. So I have actually just tried that. And if I run the unit test, you'll see that it's going to do some comparison and the values have nothing to do between them. So what is failing is this test here. Okay, so yeah, I was expecting a validation error, but in the end, no. I guess it's because really when you do a copy from a buffer to a texture, this texture layout that we have here, texture data layout, is really going to tell you, okay, what is the shape of the data that you have in the buffer, but it doesn't have to match the shape of the texture itself. It just needs to be bigger, basically. And we'll come back to that when it comes to reading the content of the texture and copying that into a buffer. So the opposite operation. I had already noticed in this case that, yeah, all you really have to have is a buffer which is bigger than your texture. And in fact, in some cases, you don't really have choice because this value here, the number of bytes per row, at least when you do the opposite, when you're copying from a texture into a buffer, it should be a multiple of 256. And so it means that if your actual texture is like 64 by 64, and you want to copy that into a buffer, your buffer must at least plan the space for 256 by 64. The number of rows doesn't have this constraint, but the number of rows, so the 8 of the buffer. But the width of the buffer, you have to respect this constraint. So it means that, yeah, the buffer is bigger. And I guess here it's what's happening. The buffer is bigger, but you're just going to take the part that you're interested in to fill your texture. This would deserve, in fact, another unit test, but yeah, I have not done that, and we'll see one day if I have time for that. Anyway, if we don't go this way and just use the half value and don't mess anything with channel size, then this unit test is working just fine. Guess I can just rebuild that quickly. Okay, I'll just rerun that. Now we don't have any error, and everything is all right. So yeah, this was it concerning this testing of the float 16 format. So in the end, in case you're wondering, is this half format here? This is coming from an external library which I'm using now. And where did I put that? Yes, in the sources for the core external. Oh, here it is. So it's coming. Let me try to find the actual page. Okay, so I think this is where I took this R file from. So you have the address of the project here, and then in the includes folder you have this HPP file. Okay. So what's next? Okay, so the next interesting thing I think we should discuss here is this mechanism here. I have just discovered that, and basically you can use that to try to wait for the work that you have spent on the GPU to be executed. So I have created my own simple wait idle function here, which is going to wait until there's nothing left to do on the GPU, and at that point you will be notified. So to achieve that, what you can use is simply this function from the queue object that you get from the WebGPU device, this onSubmitted work done. And this is going to take basically just a callback here and user data. And this will be executed when, as far as I understand, when all the work that was submitted to the queue before you call that is done, but not necessarily all the work that was submitted to the queue after you call this function. At least that's what I think it is. I'm not completely sure about that. To be checked one day. So yeah, the idea is when you call that, you know that everything that was submitted before is completed. So if you want to wait until there's nothing left to execute, all you need to do is at the time you want to stop waiting, you post such a callback. So you post a submitted work done callback, and from that point you just wait like what we're doing here. We have a simple Boolean atomic value, which is false by default, and when the callback will be executed, it's going to set this Boolean value to true, and you're just going to wait for that. And while waiting, there is another critical thing to keep in mind. You still want to be processing the events that you get from the WebGPU device itself. So I think the function I have is coming from the instance. Let me just check that. So WebGPU, come on. Process events. Yes, this is just going to call this WebGPU function on the instance, the down instance in my case, because we are on native WebGPU. I guess it's the same when you're running in a browser to be verified again. And yes, so if you don't process the event, basically your callback here will never be called, so you're going to wait infinitely. So be careful about that point. Also, a small note that I gave to myself is that here you have what is in fact a signal value in the function nature definition, and I had no idea at first why this was here and what you're supposed to do with it. And I just actually been checking the unit test that you have in the down library itself. And from what I understood, this value for now should really just be 0. And if you try another value, it's going to fail. I have not tried actually, but from the unit test perspective, yeah, if you set this to 1, for instance, it's not going to do any good. Okay. Another thing that I want to mention maybe is this function is in fact pretty interesting. I'm not really using this to the full potential for now, but what you could do with that, for instance, is you could submit some work to the queue, and then you use this submitted work down callback system to get notified when some preliminary work is done. And at that point, maybe you can continue with submitting additional work, and then you could use additional callbacks like that. And you could actually build a complete asynchronous structure of different work packages that are submitted one after another, depending on dependencies that you will have between those packages. So something to keep in mind for later when we get in very complex stuff, I guess. But for now, we don't really need that. I mean, I don't really need that. Final thing I wanted to mention, which is not related to all what we have been discussing so far, is this point. When I was introducing the changes from the previous recording, in case you remember that, changes on the log manager. Yeah, sorry, what was I saying? Yeah, when I was working on the log manager updates, I was only building for desktop. So using actually C9, I'm not even sure I've tried with MSVC. I should probably try that. But then at some point I had to upgrade one of my unscripted project, and I just realized at that point that the usage that I have for the blocking concurrent queue is not compatible currently with unscripting. At least I had a compilation error that I could not find how to resolve properly because it seemed that this symbol here is missing. It could be that maybe if I use an updated version of unscripted, it would be fixed. But with the version I have, this was an error. So I had to kind of disable usage of this blocking concurrent queue while I'm building for unscripted. Not really a terrible issue, but I need to get back to this at some point to improve on this a little bit. Just, yeah, so you know. Apart from that, yeah, I was trying to investigate a bit how we're supposed to create those tiles in the Elevation Producer. So I've been reviewing most of the code that we have in there, and I've been trying to re-implement that step by step. So this producer, there's nothing really too fancy about it if you start to understand what's happening. Apart from the part where you're going to create the tiles themselves. So not going to go into too much details, but basically you have a few functions that are used to start creating the tile. Everything on this is going to be based on a create tile class, a dedicated create tile class. So I implemented that. So you start creating the tile, then you do actually create the tile, and then you end the creation of the tile. Basically, when you start creating the tile, you're going to request all the resources that are needed to build your tile. And then in the end, create tile, you're going to release those resources. But the real work then is going to happen in this do create tile function. So I spend most of my time so far focusing on this part. And also what you can see already here with the construction is that it depends on a lot of stuff that are directly related to OpenGL itself. So we have a frame buffer, for instance, here. We have a few textures that are OpenGL textures, and you're already starting to define some uniform values like that. So yeah, that's going to be requiring quite a lot of changes. So as I said, start create tile. That's where you get the tiles. And begin create tile. I'm not using it anymore because when this was implemented, I guess you were using OpenGL anyway. You have to start with a frame buffer and make that frame buffer current, render your tile, and then you would move to another frame buffer. But in our case, we don't really need this frame buffer system. In fact, everything containing the frame buffer from OpenGL is something that is going to be replaced with a render pass in WebGPU. Because the idea with the render pass is really to define what is going to be your target, where you want some rendering to happen. So you want to render something into a given target. And that's the point of the frame buffer was used previously, I guess. This is in fact what I'm starting to mention here. The idea was to focus on replacing the frame buffer with render pass. So let's try to make it do the do create tile function. So in this one, yeah, things start to get messy. This function is going to be executed as part of a task. So it could be executed on different threads. And you could have multiple, well, not really because it was a GPU function, so I guess only one of them could be executed at a given time. Probably. Not quite sure. So in there, you're going to start populating. You see, for instance, some of the uniforms. Actually, all the uniforms. You're also going to link the texture that you want to use to create the tile. So with those simpler uniforms, there's one here, another one here. Another simpler, another uniform vector here. And this is going to set up some noise details. And again, you're going to provide that with the noise texture and then the noise vector. So you prepare all the uniforms. And then you have the current frame buffer, which was assigned as part of the begin create tile. And you're going to draw a quad using your upsample program. It gets even more messy than when you have layers, but currently I'm not really focusing on that part. And then when you're done with that, what you do is you copy the content for your frame buffer, so what you have rendered on your target, into your destination file, if you want. Yeah, pretty tricky. Okay, so the idea, as I said, was really to try to replace that frame buffer we just discussed with a render pass. So we're going to set up a render pass, defining where we want to render some content. And then in this render pass, we're going to add a render node, because the render node is what we use to define a pipeline. So defining what is going to be the shader that will be executed. So we need a single render node because we only have a single pipeline. Here we're just going to render this up simple program. I can just show you actually what this simple shader is looking like. So you see this one is going to accept different uniforms. These are the uniforms that were set up just before, as we discussed. And you have a vertex shader, which is just going to do nothing about rendering a full screen quad. And then you have the fragment shader, where you have some stuff happening, which I'm not understanding yet, really. So I need to spend some time on that, but you're going to render the content you want for a given time. So, and also, as we can see here, when you render on your target, you're not directly writing to your destination type. So how can I explain that? The end idea, if you want, is really that you have a tile storage, which is a texture to the array. And in this texture to the array, each layer is a single tile. You want to be able to update those layers separately. So what you could do maybe would be to create a render pass where the target is exactly the layer that you want to update into this texture to the array. And then you do the rendering and you will get your layer updated. Problem if you do that is that whenever you want to update another layer in the subtexture to the array, you need to update the render pass itself. You need to recreate the render pass with a different target. And this, I believe, is not very good. And I'm ready to bet that it's more efficient, in fact, to have a render pass rendering into an auxiliary texture to the texture, which is fixed. And you do the rendering, and when you're done with the rendering, you just try to copy what was just written into this target texture into the layer of interest that you wanted to update. If you do it this way, you don't have to update the render pass at all. You just create that once, and the target texture is not changing. It's always the same, so you can just reuse your render pass continuously. And actually, this is a bit what is already done here. We're not rendering directly to the GPU data, which is actually pointing to the layer of interest in the 2D array, in the texture 2D array. We are going to render to an additional texture and then copy the output into this layer. Okay. Oh, I'm just, yeah, I didn't show the code. I was talking about that. So you're rendering to your frame buffer and you're doing the copy. And what else should I mention about that? Okay, the thing is, in the initial implementation, this would only really happen on a single thread because OpenGL was not free safe and you could not really do this from multiple threads at the same time. But on our side with GPU, we can actually do that for multiple threads at the same time. So you could be, in fact, rendering multiple of those elevation tiles at the same time. And how are we going to do that? My initial idea was to just try to use a spin lock. In fact, I was trying to use a spin lock, but you could use a mutex also to synchronize the access to everything. But then I realized you don't really need to do that. What you could do instead is you take for granted that you are going to execute that on multiple threads. And what does it mean? It means that you need to be able to set up everything that you have to set up to prepare a command buffer independently on those different threads. And for that, I think the best option would be to use thread local storage or thread specific storage so that you don't really need to synchronize anything in the end. So I quickly actually moved in this direction using a simple technique like what we have here. The idea here is you can get a thread ID for different threads, and this ID is going to be incremented progressively from 0. So all the threads that are going to call this function are going to get an ID which is 0, 1, 2, 3, 4, 5, and up to the number of threads that are going to call this. So if you can have that, then what you can do is what we have, no, not here. The ElevationProducer. What we have here, no, let's go. Let me just check that. This function, whenever it's time to create the tile, you get the thread specific data. And then once you have the data, you don't need to interfere with any other thread. So you don't need any kind of synchronization system. And yeah, when you do that, you actually create your render pass per thread. You create your uniform buffer also per thread, and then you submit a command buffer per thread again. And yeah, this recording is already too long. I really wanted to go a bit further, but I guess I'll keep that for the next time then. Yeah, let's do it this way. Next time we'll try to get into more details on the code exactly on how we have implemented this per thread data storage and what we currently have to yeah, to create the node and bind the groups and so on. Okay, let's cut it here and we'll resume in the next recording. So see you next time. Bye.